Welcome to the Deep Dive, where we plunge into cutting-edge research to bring you the most important insights, minus the jargon. Today we're uncovering some of the unseen heroes of engineering. We're talking about the advanced materials that make everything from the cars we drive to the aircraft we fly faster, stronger, and, well, incredibly durable.
Yeah, and these aren't just small tweaks. We're really looking at fundamental shifts in material science, things that push the boundaries of what's possible. It's all about building materials that just perform better, opening up whole new possibilities.
Absolutely. And our mission today is to take a deep dive into one of these really fascinating areas, metal matrix composites, or MMCs. Our source is a recent, very cutting-edge research paper. It was published just this past August 2025. And this paper meticulously investigates how the size of reinforcing particles profoundly impacts the material's mechanical behavior and its resistance to wear. It's quite specific.
Right. So think of this as your shortcut, really, to grasping the nuances here. We're going to break down why something as seemingly simple as particle size is absolutely critical in designing the next generation of high-performance materials.
Okay, let's unpack this then. To start, maybe baseline, what exactly are metal matrix composites?
Okay, so MMCs are, well, they're a novel class of materials. They creatively combine the best of both worlds, you could say. You get the ductility and toughness you typically find in metals.
Right, the bend, don't break aspect.
Exactly. But you combine that with the high strength and stiffness you find in ceramics. So metal flexibility, ceramic robustness, all in one material.
That is quite the combo. What kind of enhanced properties are we talking about compared to, say, just standard metals?
Oh, quite a list. You get superior specific strength, that's strength to weight and stiffness, impressive wear resistance, better corrosion resistance too, plus a high elastic modulus, and they can handle much higher surface temperatures. Yeah, so that's why they're becoming really important across research, tech, innovation, and industry, from everyday things to really extreme environments.
Now, this study focused on two specific materials, Al7075 and boron carbide, B4C. Why this particular pair? What's special about them?
Right, so Al7075 is a specific aluminum alloy. It serves as the matrix phase, which is basically the base material. It's chosen because, well, it's used a lot in demanding sectors. Think civil engineering, cars, aerospace, marine applications. Largely thanks to its high corrosion resistance. It's a really solid, reliable foundation.
Okay, so that's the base, and then they reinforce it with B4C.
Exactly. B4C boron carbide is an extremely hard ceramic, and that acts as the reinforcement. Adding these B4C particles significantly boosts the alloy's strength, its wear resistance, corrosion resistance. It even helps lower the density.
Lower density, that's huge for planes, right?
Absolutely. Big advantage in aerospace where, every gram counts.
So we've got this strong corrosion-resistant base boosted by a super hard, lightweight ceramic. But here's the core question the research tackled. Does the size of those little B4C particles actually make a difference? I kind of just assumed more reinforcement is always better.
Yeah, that's a pretty common assumption. And historically, people used micro-sized particles. They definitely add strength. But there's often a trade-off. If you add too many of those micro-sized ceramic bits, you can actually make the material less ductile, more brittle.
Ah, okay.
But here's what's really interesting now. Using nanoscale inclusions of ceramic particles, that's emerging as a way to actually enhance ductility, fatigue strength, and even high-temperature creep resistance.
Enhanced ductility. So smaller makes it stronger and tougher.
In many cases, yes. It seems counterintuitive, but that's what the research is showing. So this study really sets up a crucial comparison, looking directly at micro versus nano performance.
That's a really critical distinction then. If micro gives strength, but might make it brittle, while nano potentially offers both. I mean, how does that change how you'd think about designing, say, an aircraft wing? Strength and flexibility are both vital there.
Oh, it changes everything. It means you're not just throwing in reinforcement, you're engineering right down at the most fundamental level to get a mix of properties that was really hard to achieve before. For something like a wing, yeah, you need incredible strength, you need it to handle stress cycles, and you need it to flex without failing. Nanoparticles really open up new design avenues there.
So how did they actually make these things for this study? What was the process?
They used a method called stir casting. It's pretty reliable, widely used for making these composites, commercially successful too. It's good at getting those ceramic particles properly bonded within the molten metal.
Stir casting. Does that just mean mixing it?
Essentially, yeah, but it's very controlled. Yeah. You preheat a crucible, melt the aluminum alloy, add the B4C particles, carefully measured, of course. Then you heat it further stir it at a specific speed for a specific time to make sure everything's mixed evenly, nice and homogeneous, and to break up any clumps of particles. That's really important for a strong final material.
Right, consistency is key. Okay, beyond the big performance numbers, I'm always fascinated by what's happening down at the microscopic level. When they looked inside these materials, what did the microstructures show? How were the particles actually behaving?
Well, first off, the B4C particles, whether they were micro or nano, they did significantly enhance stiffness, mechanical properties, and wear resistance. And that's because they create these strong bonds within the aluminum matrix, which helps transfer load effectively.
Okay. And I read something fascinating about dendrites, these tree-like structures that form when the metal cools.
Yes, that was a neat detail. The B4C particles actually decrease the average length of those dendrites. That leads to a finer, more refined grain structure in the material overall.
A finer structure usually means stronger, right?
Generally, yes. But here's a little surprising twist. While the nanocomposites were superior overall, the micro-sized B4C particles were actually observed to refine those dendrites more effectively than the nano ones.
Really? Why would the bigger particles be better at that specific thing?
The researchers think it's down to wettability. Basically, the microparticles integrate a bit more easily into the molten metal. Nanoparticles have very high surface tension, which can make them harder to disperse perfectly and integrate smoothly compared to the micro ones in that specific regard.
Oh, interesting nuance. Okay, what about porosity, those tiny voids or gaps within the material? That sounds like something you'd want to minimize.
Definitely. Porosity is a critical factor for material integrity. And the key finding here was pretty clear. Nano-sized particles typically resulted in lower porosity.
Lower porosity with nano, why is that?
It's mainly their size. Because they're so small, they can disperse more effectively throughout the matrix and fill in the tiny spaces between the solidifying metal grains more efficiently. This leads to a denser composite with fewer voids, fewer potential weak spots.
So lower porosity means a denser, more consistent material. Thinking about critical parts, does more consistent basically mean fewer unpredictable failures, like having a solid foundation versus one with hidden cracks?
Precisely. Fewer voids mean fewer places where cracks could start under stress, so you get much more reliable, predictable performance. It's all about that microscopic integrity.
Makes sense. All right, let's talk mechanical properties. Hardness the material's resistance to getting dented or scratched.
Okay, so the MMCs they developed across the board showed a pretty significant jump in hardness, about 16% harder compared to the base AL7075 alloy. But the really clear trend, what we could call the nano advantage, was that hardness increased as the particle size decreased. The nanocomposites were consistently harder.
Smaller particles, harder material. What's the mechanism? Why does that happen?
Well, imagine trying to push something through a tightly packed space. If the obstacles are small and numerous, they resist that movement more effectively, right? Nanoparticles act similarly. They effectively hinder the material's ability to deform or flow under stress. They also create more interfacial area, more connection points with the matrix, which helps the composite absorb external loads more efficiently.
Okay.
Larger microparticles, on the other hand, while they might help with ductility, they showed lower resistance to that kind of dent deformation.
And tensile strength. How much pulling force can it withstand before it breaks?
Again, an overall improvement. The MMC showed about a 13% increase in tensile strength compared to the base alloy. And here, too, the nano B4C particles really shone. They significantly enhanced both tensile strength and wear resistance.
Why was nano better for tensile strength?
It seems to be down to a couple of things. More efficient load transfer within that metal matrix, like we saw with hardness. Also, a reduction in stress concentration points. And importantly, nano B4C also helps refine the grain structure of the aluminum itself. This is a well-known strengthening mechanism. It relates to something called the Hall-Petch relationship.
Hall-Petch, right. That basically says smaller crystal grains make the metal stronger.
Exactly. Smaller grains mean more grain boundaries, which act as barriers to dislocation movement, making the material harder to deform permanently. So nano helps on multiple fronts for strength.
Okay, that makes sense. Smaller grains, stronger material, nano seems better. But did the study find anything maybe counterintuitive about how the micro-sized particles behave during those tensile tests? Any surprises there?
Yes, actually, a very important one. The study found that the composites with micro-sized particles collapse more quickly during tensile testing than the ones with nanoparticles.
Never quickly. Why?
Two main reasons proposed. First, those larger microparticles have a bigger interaction area with the matrix. This can actually lead to greater stress concentration right around the particle.
Ah, like a weak point magnifier?
Sort of, yeah. Second, statistically, a larger particle has a higher chance of containing an internal flaw or imperfection that's big enough to cause problems, a critical size flaw. So they're just more likely to fracture internally under load. And once those reinforcing particles break, they're no longer reinforcing, they become defects, weak points. That leads to a faster decline in the composite's overall strength.
So even if they seem strong initially, those bigger particles can actually become the Achilles heel under serious stress. What did the fracture surfaces look like under the microscope? Did that confirm this?
Oh, definitely. The visual evidence was quite striking. When they looked at the broken surfaces, the composites reinforced with the larger micro-sized particles showed multiple cracks, a brittle kind of rupture. It looked like things had just snapped.
Consistent with the particles cracking.
Exactly. But in stark contrast, the composites with the smaller nano-sized particles, they showed a fracture surface that looked almost ductile. You could see these little dimples on the reinforcement particles. It indicated a much more resilient, tougher failure mode, not just snapping, but stretching and tearing a bit first.
That's a really clear visual difference. Powerful evidence for the nanocomposites being more robust. Okay, let's switch gears slightly and dive deeper into wear. How things hold up against rubbing and friction. How did they test that?
They used a standard piece of lab equipment called a pin-on-disc tribometer. Basically, you take a pin made of your composite material, press it against a rotating steel disc with a constant force, and measure how much material wears away from the pin over time, usually by weight loss.
Okay. Standard wear test. And what factors did they vary?
They focused on three key things. First, a particle size, obviously micro or nano. Second, the sliding speed, how fast the disc was spinning. And third, the sliding distance, how long the test ran for.
Right. So what were the main findings on wear loss? How much material actually disappeared? Which ones held up best?
Well, particle size was definitely dominant again. The nanoparticulates consistently showed better wear resistance. Less material was lost compared to the micro ones.
And why was nano better for wear?
Several reasons suggested. The fine particles are just more widely and evenly distributed. Their sharp edges might get dulled during the abrasion process itself, and maybe crucially, they seem to embed better into the matrix, making them less likely to get pulled out or fragment.
That makes intuitive sense. Less likely to get ripped out. But here's where the study had some results that seem, well, backwards, for these specific composites anyway. What did they find about sliding speed and distance affecting wear?
Yeah, this was really interesting and, like you said, counterintuitive. They found that better wear resistance, meaning less wear, was achieved at higher sliding speeds.
Higher speed, less wear. Usually you'd think faster means more friction, more heat, more wear.
You would. That's the typical behavior for many materials. But for this specific AL7075 B4C system, the results suggested something else is happening. It might be related to specific changes in strain rate sensitivity or friction heating effects at the interface that actually make it more resistant at higher speeds. It's quite specific to this material combination.
So the fact that higher speeds can sometimes reduce wear here, I mean, that's potentially huge for designing high-speed parts, isn't it? Maybe you don't always have to trade speed for durability.
Exactly. It really challenges the conventional thinking for this system. It could open the door for designing faster-moving components, maybe in engines or bearings that are actually more resilient than we thought possible. Longer life, less maintenance, potentially.
Okay, what about sliding distance? Did that also have a surprising effect?
It did. Increased sliding distance also led to better wear resistance, less wear over a longer test.
Again, kind of backwards. You'd think more sliding equals more wear.
You would. But the thinking here is that a couple of things happen over longer distances. First, a protective oxide layer can form on the pin surface, acting like a shield. Second, the wear debris generated the tiny bits that break off can actually get compacted into the valleys of the surface texture.
So they fill in the gaps.
Yeah, they effectively smooth out the surface at a microscopic level, reducing further abrasive action. The material sort of creates its own protective layer and smooths itself out as it wears.
That is remarkable. Material that gets tougher the longer it runs, in a way. Okay, what about the coefficient of friction, the COF? Basically, how sticky or resistant the surfaces are to sliding against each other.
Right, friction. Here, the COF decreased as the particle size was reduced. So nano had lower friction.
Why lower friction with nano?
The larger microparticles tend to create more noticeable bumps or asperities on the surface. That means more points of contact, more interlocking, hence higher friction. The smaller nanoparticles embed more uniformly, they don't stick out as much, leading to better load distribution across the surface and just fundamentally lower friction. Smoother sliding, less energy lost.
Okay. And how did speed and distance affect friction? Was it complex like the wear rate?
A little less surprising here. The COF decreased with increasing sliding speed.
Why is that?
That's likely due to the heat generated at the contact point. Higher speed means more heat, which can slightly soften the very surface layer of the material, making it easier to slide over, like putting skis on warmer snow.
Okay. And distance?
The COF increased with increasing sliding distance.
Ah, the opposite of wear rate.
Right. And that's probably because, over longer distances, more wear debris accumulates between the surfaces. While some fills valleys, excess debris can act like grit, increasing the frictional forces.
So a really complex interplay of factors. But when they did the statistical analysis, the ANOVA, was there one factor that really stood out as controlling wear and friction above all others?
Oh, absolutely. The statistics delivered a very clear message. Particulate size was overwhelmingly the most significant factor for both wear loss. It accounted for over 61% of the variation they saw, and also for the coefficient of friction, again, over 61% of the influence.
Over 60% for both.
Yes. It means that for these specific composites, how big those B4C particles are is by far the primary driver of how they perform under wear conditions. Size really is king here.
Size is king. Got it. Okay, let's talk about the surface itself. What did the microscope show after all this rubbing and testing? Starting with surface roughness, how smooth or rough was it?
Well, again, nano came out on top for smoothness. The nano-sized particles tended to reduce the surface roughness both before and after wear testing.
Why smoother with nano?
They fill in the microscopic gaps more effectively, as we discussed with porosity. And because they're harder and smaller, they resist being deformed or pulled out during polishing or wear, leading to a smoother finish.
And the microparticles?
They led to larger surface roughness, partly because they don't disperse as evenly, which can weaken the bonding at the interface. And the larger hard particles themselves create bumps and act like abrasive points.
Did that difference hold up after the wear tests?
Generally, yes. After wear, the nano-reinforced MMCs often stayed smoother, especially if the sliding distance and speed weren't too extreme. The microcomposites, though, they often showed a big increase in roughness after wear. You'd see pits and little craters where particles had been dragged out or fractured.
Right. And the pictures from the scanning electron microscope, the SEM images of the worn surfaces, I imagine they told a clear story. What did the nanocomposite surfaces look like?
They looked remarkably good, relatively speaking. Much smoother surfaces, minimal damage, just fine wear scars. And this goes back to that uniform dispersion, the improved grain structure, better stiffness and strength. It all helps distribute the stress better. But crucially, researchers think the nanoparticles also activate these anti-wear mechanisms. They help form a protective layer right on the wear surface, sometimes called a tribofilm.
A tribofilm. So the material essentially builds its own shield against wear as it's happening. That sounds amazing for durability. Where would that be most useful?
Oh, think about components in really harsh conditions. Maybe marine propellers constantly churning sandy water, bearings in aerospace engines, parts in heavy industrial machinery. Anywhere where it's just a constant battle. This tribofilm acts like a shield, protecting the underlying material from further damage, preventing particles from getting pulled out. It leads to significantly less material loss over time. It could drastically extend the life of critical parts, cutting down on maintenance, replacement costs. It's a big deal.
A huge deal. Okay, and the microcomposites under the SEM, what was their story?
A much rougher story, literally. They showed things like shallow plowing grooves where material had been gouged out, and delamination cracks where layers were starting to peel away, just signs of more severe wear.
And why such severe wear for micro?
It's likely due to higher strain levels right at the particle interface, that stress concentration we talked about, weaker bonding between the big particles in the matrix. All this can cause the matrix material to crack or the particles themselves to break or get dislodged. You end up with these irregular wear tracks and much more material flying off. It really highlights the dramatic difference in how these materials fail under wear.
Wow, yeah. It really paints a picture of very different behaviors at that tiny scale. So zooming back out then, what's the big takeaway? What does this all mean?
Well, the overarching conclusion is pretty clear. For this AL7075 B4C system, the nano-reinforced composites generally outperform the micro-reinforced ones, pretty much across the board. Better mechanical properties like hardness and tensile strength, better wear characteristics, lower wear loss, lower friction, smoother surfaces after wear, and a tougher, more ductile way of fracturing instead of just snapping. And that ability of the nanoparticles to help form that protective tribofilm, that seems to be a real game changer for wear resistance and making parts last longer.
So why does this research matter to you, our listener, maybe an engineer or designer out there?
Well, it's vital information if you're trying to select or create materials for demanding jobs. Things that need to be not just strong, but also really durable and wear resistant. Think critical components in buildings, bridges, cars, planes, ships. This shows how incredibly precise material design, right down to the particle size, can lead to materials that just perform better and last longer. That ultimately impacts reliability, safety, and cost effectiveness across loads of industries.
And you mentioned the cost aspect earlier. B4C isn't cheap, right? So this research helps use it smarter.
Exactly. The paper mentions the high cost. So by figuring out the ideal particle sizes in this case, nano seems best for many properties, and potentially optimizing the weight percentage, this kind of research helps make sure you're getting the performance benefits that justify the cost. It helps move these advanced materials from the lab bench into real-world applications more effectively.
Okay, so to recap our deep dive today, we've really seen the profound and sometimes quite counterintuitive impact that particle size nano versus micro has on the strength, the toughness, and especially the wear resistance of these advanced metal matrix composites. It's precision engineering at its finest, isn't it? Manipulating things at the nanoscale to get huge performance gains you can actually see and use.
It really is, and it makes you wonder, doesn't it? As we keep pushing the boundaries of material science, seeing these kinds of advancements driven by something so fundamental, what's the next frontier? What comes after just optimizing size?
Yeah, are there maybe further secrets hidden in the particle shapes? Or specific surface treatments for the particles? Maybe even designing multi-layered composites? Could unlocking those secrets give us even greater potential?
Could it perhaps make these high-performance materials cheap enough, reliable enough, to be used in even more revolutionary ways we haven't even thought of yet?
Lots to think about. We hope this deep dive encourages you to look at the materials all around you, maybe with a bit more appreciation for the incredible science and engineering that makes them possible.